do this again. Take two. Ready? All right, hello everyone. We are the Advanced Combustion Technology team. My name is Laszlo Kurda.
I'm Chris Jenkins.
And then Lam wasn't able to make it today, so there's the team. Let me begin by giving you guys a little overview of the presentation, give you guys some background about what we're doing, our goals and objectives, what we accomplished this year, what we've learned, and then future work going forward. So we give you guys some background about small internal combustion engines. Those would be considered engines that are 50 cc or less. They're used in various applications such as power, gardening equipment, mobile power generators, and scooters, transportation around the world, especially in developing nations. Unfortunately, there are no stringent emissions regulations on engines of this size. Thus, that makes these engines of this size large contributors to global pollution. One avenue to alleviate the pollution issue is by implementing advanced combustion technology to engines of this scale. One form of that technology is called HCCI, homogeneous charge compression ignition. Chris will get more into details on what exactly that is.
Thank you. So HCCI was kind of the big goal for our project. We wanted to be able to test an HCCI system on a small scooter engine. And so the reason HCCI is important is because every vehicle that we have nowadays, or most of them, like cars, motorcycles, scooters, trucks, they're all propelled by reciprocating engines. And so we have the diesel and the Otto cycles. Those are the two most common ones. And so what an HCCI system does, homogeneous charge compression ignition, it takes the best components of both of those, so the diesel cycle and the Otto cycle, and mashes them together. But when you do that, you get a whole new set of challenges in being able to control and properly burn that fuel. And so if you look over on this diagram over here, this is the diesel range up here. You get a lot of soot, which is just carbon chains that haven't burned, so carbon fuel that hasn't burned. You get a lot of soot production. And over here is the Otto cycle region, which is characterized, you get lower soot, but you have a very high combustion temperature, which produces nitric oxides. And so HCCI aims to be able to lower the combustion temperatures into this region right here, but also reduce the soot production and nitric oxide production. So for goals and objectives, the goal of this project, we wanted to make a small scooter test bed. So not just for HCCI stuff, but we want to be able to test it for anything we wanted. We wanted to have a very versatile platform where we could test HCCI, but also other things as well. And so we have the big goal is the engine test bed. So in that we have that broken down into several small objectives. So we have the dyno and the stand, the throttle control, the sensors, and the DAC, so the instrumentation, and then the emissions analysis. So this is, before I get into the objectives, the engine specifications we have. We started with this, it's a 2013 Yamaha Vino Classic. It's a 50 cc single cylinder 4-cycle engine. It produces a whopping 3 foot-pounds of torque. For anybody that knows cars, it's not very much. It'll probably top out about 50 miles an hour or so. And so that's the scooter that we have to work with. It's also fuel injected, so it's electronic fuel injection.
So this was the project timeline. Basically, all the objectives are in blue, the major 4 objectives, the major milestones are in between. This is the timeline we had in place at the beginning of the quarter. This is what we wanted to achieve. So by the end of the quarter, we essentially wanted to have emissions analysis completed. Now the reality of what we got done, next slide, is this. So the dyno and stand objective is 100% done. Throttle control, which was essentially the most tedious portion of all our objectives and the most time-intensive portion is also complete. The sensor and data acquisition portion is about 50% done, and we never got to the emissions analysis, unfortunately. So let's get into a little more detail. So once again, the structural portion, which is the work stand dyno chassis, this got completed in the fall quarter. It was straightforward, simple, essentially hold the bike upright while it's on the dyno so we could get testing done on it. And that also included rewiring and color coding the wiring as well, so that we have easy access to inputting it into the DAC.
Yes, the second objective is the automatic throttle control that Laszlo mentioned. That was the biggest portion of this project. And so that required several things. We had a mechanical design portion as well as a coding portion. We want to be able to have this be autonomous. And so if you look, this flow chart kind of describes our thought process when we were designing our code, our Arduino code. We used an Arduino microcontroller to control that servo for the throttle. So this flow chart is kind of the process we use to figure out how we want our code to go. We need some sort of feedback system to be able to control the speed of the scooter, because the scooter doesn't have a mechanical transmission. It's got a slipping transmission. So depending on load, you can give it different amounts of throttle, different RPMs, and it'll still go at the same speed. So if you have very high load, it takes much more throttle to be able to keep the same speed as a low load situation. And so we needed that little feedback loop to be able to keep the scooter running at the same speed. So this is a rendering. So on the left side, that's the actual scooter. So that's the mount point for our throttle control. On the right side is a CAD rendering of what our throttle control looks like. So we have the servo, this adapter we machined to index with this hole right here, and then this is our mounting plate that mounts to these two screws right here. So there's one here, and there's one, you can't really, I'm sorry, it's right here and right here. So that's where that plate mounts, that's where the servo mounts. And this is a picture of it all mounted up, and so you can see it mounts to these two holes right here. The servo's here, the bracket is kind of pictured right here, and then that little adapter we made to fit on the end of the throttle plate is pictured.
All right, so sensor and DAC, why do we need this? In order to achieve HCCI, we need to be able to control certain in-cylinder variables, including intake pressure, coolant temperature, crank composition, intake pressure, in-cylinder pressure, air-fuel ratio, and exhaust temperature. We're going to interface that with a LabVIEW code, so that was going to be basically the heads-up display, so we see what values we're getting. That is complete. We completed that. The LabVIEW code is complete, as you can see, essentially outputting all the variables that we need. We'll go on to the next slide. Unfortunately, we ran into some issues. One of them is the pressure transducer that we already had just was no longer functioning, just wasn't working. And it's quite expensive. It's around a few $100, or was it $1,000? I think it was around $1,000 to replace it, and we just didn't have funding, and we were advised to just move on past that. So that's something that needs to be done in the future and taken care of. The O2 sensor, which we're going to use to measure air-fuel ratio, the one we have was not compatible with the scooter tailpipe, so that's something that's going to have to get resolved as well. And then we had a weird anomaly where we would, for throttle position, the LabVIEW code would work when the engine's not on. So we'd move the throttle and it would give us an output. But the minute we turned the engine on, it was just extremely noisy and it was just all over the place, and we really didn't have a chance or time to figure out what's going on. So that's another issue that also has to be taken care of in the future. And then we can move on to the next slide.
All right, so the fourth objective, that's the emissions analysis. So we had two criteria for that. We wanted to have a baseline emissions analysis, so just the scooter running at certain RPMs, either unloaded or just statically loaded, and we would be able to take a baseline emissions from that and be able to compare that for whatever tests we did later on for any combustion technology we performed. And also an autonomous testing, so that's where the Arduino and the throttle control came. We wanted to be able to run certain load cycle and RPM sweeps, so we wanted to have it just programmed to go a certain speed at certain loads and just completely run without us touching it. Just so there isn't any human error, we don't have to modulate the throttle by ourselves, it goes by itself. So we ran into several problems with that because, well, first of all, we didn't get our scooter into a place where we could actually run it. It was indoors for the longest time. And we didn't have a spot to put it until about 3 weeks ago, I'd say. And so we actually hadn't run any of our systems because we couldn't use it unless we had the scooter running, which we couldn't run it because we had nowhere to run it. And so we still haven't found a place where we can set up our dyno. So our dyno takes a 220 power plug, and so nobody has a 220 power plug. We've been trying to get one wired, but we've been told it'll take 3 to 4 months to get it going. And so we haven't been able to get any emissions analysis because we haven't been able to run our scooter. So that was kind of the source for a lot of. That's actually also why we had that noisy throttle problem. We developed this whole system with the scooter not running because we couldn't run it. And then all of a sudden we turn it on and nothing works. And so that was one of the things that we got from that. But so the emission analysis is something that we kind of pushed until either summer or next year, fall quarter, when Tony, our grad student. And so those were some of the problems we had with that.
So our experience. What did we learn? I think it's obviously individual for each one of us, but generally we all learned about HCCI. Arduino coding for sure. We did a little bit of that in a few of our classes, but never to this extent. Sensor electronics, which I've never really dealt with up to this point as well, and then LabVIEW, just learning it and implementing it. Me personally, on top of that, those are the technical kind of skills that I gained from this. I also got really good at presentations. I didn't know it's true. I got good at presentations. I was project lead, so management issues. And we had a small group, so it wasn't really, I didn't have to delegate too much. It was nice. We were able to kind of work together, but just other things, Gantt charts, stuff like that, time management. But
yeah, so for me, again, it's all individual. So for me, it was, I guess it was more of a learning process. It was kind of a good shocker at the kind of bureaucratic process. Because like I said, we had so many problems getting everything to work, function, correctly, as well as not just that, but scheduling meeting times between three busy college kids and a professor and an advisor, as well as a grad student. It's really hard to find time where everybody's available that isn't, it's just some normal working hour during the day. So that was one of the things we kind of ran into, but also that, it's just I guess the scale of the project. I guess maybe, I'm not sure if we took on too much or we had too lofty goals, but we had a lot of things that kind of stopped us from achieving what we really wanted to achieve. One of the things that I was really hoping to do with this was actually do some combustion testing and analysis, but we didn't quite get there. We just built the test bed. And so I guess that was one thing that I was a little bit disappointed by. But also, other than that, the programming LabVIEW and Arduino, that was a venture in itself. I'd never done much of that before, so that was interesting to get more experience with. And also, outfitting sensors and instrumentation on the test bed was a different sort of hands-on experience.
And I think what we also ran into is a lot of things, it was out of our control, things that held us back. For example, the dyno, since beginning of last quarter, we were trying to find somewhere where we could plug this thing in and it could work. And there's nowhere. We couldn't find anywhere with that at a 220 and 60 amp plug, or outlet, excuse me. And there's nothing we could really do about that. So finally, they have to rewire the actual infrastructure within Gateway just for us, so that we can have an outlet for our dyno. And that's something, so in retrospect, this dyno was passed on to us. So if whoever was working on this the previous year, they'd have done a little more research and maybe done a dyno that works with the outlets that we have. That would make things a little easier. And there's other things, that kind of wasn't really in our control that really showed us that, hey, a curveball can be thrown in and you really have to just kind of adapt and go with the flow.
All right, so with that, is there any questions?